Unit 8, oxygen-containing compounds. We're going to cover a bunch, 4 or 5 different types of functional groups today. We'll go over their naming protocols. Some of them are going to have reactions that we want you to know. Some of them aren't. So we'll give you those as well. The first, under our oxygen-containing compounds, are going to be our alcohols. Alcohols. Now, alcohols have a functional group that is an OH group attached. You okay? You sure? What's that noise? Okay. This R is a general term for alkyl group. Alkyl group. And we know from last lecture that an alkyl group is any of those 10 alkanes. There's more alkyl groups, but for us, you take an alkane, you remove a hydrogen to create a point of attachment, that's an alkyl group. So any of those first 10 alkanes, remove a hydrogen, and you have an alkyl group. What this basically says is that this has to be a carbon. Okay? It doesn't necessarily matter, how branched it is or how long the carbon chain is, but you have an OH connected to a carbon. That's going to be your alcohol functional group. Now, we've seen OHs, right? We saw them in bases. We looked at our definitions for an Arrhenius base. It was an OH minus producer, right? Anything that produces OH. The difference here is that the alcohols are bound to carbon, whereas the bases were bound to metals, right? So, covalent compounds versus ion. The OH group is polar. Okay, if I expand it a little bit. Okay, I remember that oxygen is in group number 6, right? 1, 2, 3, 4, 5, 6. So it wants to form 2 bonds, and it has 2 lone pairs. Okay? And if I recall, that geometry is bent or angular. So I kind of drew it that way. We put our 2 pairs of electrons in there. We can see that the OH group is polar. Okay? And this is no different than water. If you can remember what water looked like? We looked at that quite extensively when we looked at hydrogen bonding. This is nothing more than water, only get rid of that and we put an R group on there. That's our alcohols. Okay. Well, the polarity of the OH group will dominate the solubility characteristics of the alcohol if it's a small chain. So if you have a couple of alcohols, okay, you see this OH group is polar, and since water is itself a polar covalent molecule, this OH group will interact very well with water. Okay, it interacts very well with water. And that's going to be the slightly positives of water interacting with the slightly negatives, or the slightly positives on the alcohol with the slightly negatives, and then, of course, these negatives over here would interact with the slightly positive on hydrogen. So when you have a small chain alcohol, small carbon chain alcohol, the OH group will dominate the solubility characteristics and it will mix with water. It will be miscible. It will form one single layer. But as the hydrocarbon portion, which is nonpolar in nature, like oil, as this gets bigger and bigger and bigger, the hydrocarbon starts to dominate the solubility characteristics, and the alcohol will actually separate out into two phases with water. Okay, we actually do that in lab. We figure out what the limit is on that carbon chain. All right, something you're going to do. But alcohols are very good, usually very good solvents, because you can kind of monitor their polarity. Right? And in the small chains, they'll interact very well with water-soluble reagents. And in their larger hydrocarbons, as they get bigger and bigger, they'll interact very well or mix very well with non-polar reagents. So they're pretty versatile solvents. There are different degrees of alcohols. And it's very easy to tell what degree your alcohol is. You look at the carbon that contains the OH group, and you say, how many other carbons is it attached to? If it's attached to one, it is a primary alcohol. And we show primary with this one, this little degree sign on it, primary. Now, it doesn't matter what's attached out here. Doesn't matter. You could have big, long carbon chains. You can have, just doesn't matter. The only thing that matters is the carbon that contains the OH group is bound to one and one only carbon. Or you could say it has two hydrogens. But it's bound to one carbon, then it's primary. If it's bound to two, it is secondary. Again, it doesn't matter what's here or here. It just matters that it's bound to the two carbons. Now remember, you're concentrating on the carbon that contains the OH group. And you will have to know this because primary alcohols react differently than secondary alcohols than tertiary alcohols. Well, didn't do tertiary yet, right? So, our tertiary alcohol looks like this. I'm getting a little close. Don't want you to confuse that. Okay? You will have to identify primaries from secondaries from tertiaries. And in fact, you might have a question on the exam that says, from the following, which is a secondary alcohol? And you have to go through and you have to figure out which one's a secondary alcohol. You just locate the carbon that has the OH, and you look and see how many other carbons that carbon is bound to. The number of carbons it's bound to will tell you the degree of the alcohol. Okay? Good so far? We're going to see them in just a minute. We're going to see primaries versus secondaries versus tertiaries. Okay? All right, naming. How do we name our alcohols? When we name our alcohols, all of our previously developed protocol for alkanes is true. We're just going to modify a little bit. Okay, we have to find the longest carbon chain, the longest continuous carbon chain. But like our alkenes and our alkynes, the chain has to contain the OH group. All right, so it's the longest continuous chain that has the carbon that contains the OH group. All right? Basically, you have to have the functional group in the parent chain. We're going to drop the E from the alkane parent and we're going to add the suffix OL. Note to self. The word alcohol ends in OL. And so do all the names of the alcohols. Okay? So the members, first couple of members of the alcohol class, we have CH3OH. Normally, this would be, the one carbon derivative would be methane, right? This is methanol. Notice we drop the E from methane and we add the suffix OL. You see how important it is to memorize those first 10? Get used to this, because this is how they all work. You drop this from the alkane name and add this. Ethane. This is ethanol. Anybody ever heard of this? Yeah, it's drinking alcohol, right? Drinking alcohol. There are common names. This is IUPAC. We're using IUPAC procedures for our protocols for all of our naming. But there are common names associated with most of these. And the common names use the name of the alkyl portion and then follow it with the word alcohol. So this would be methyl alcohol. That's the common name. And I didn't give myself enough room. So let's move this over. Did it. I had to write on the metal, but I did it. This one would be ethyl alcohol. Okay, again, they're just naming the alkyl portion. Sometimes the common name can't be used. Okay? If you have an 8-chain carbon, 1, 2, 3, 4, 5, 6, 7, 8, and then you have the OH here. I mean, with all the hydrogens on there, is that an alkyl group? Yeah, it is, because technically you took the octane, you removed a hydrogen, and you planted the OH on there. But what's the name of that alkyl group? It does have a name, but we don't care about it. So these common names are generally only good for the shorter chain alcohols. Probably going to stop, somewhere around butyl. What's that one? Propanol. Okay, hold that thought. What's this one?
Is it isopropanol?
Well, they're both 3 carbon chains, right?
Mm-hmm.
Okay. So once you get to 3 carbon chains, if you want to use IUPAC, you have to locate where the OH group is. So again, the longest carbon chain here is 3. This is a 3. The OH group is on carbon number 1. Right? So this would be 1 propanol. Because that one can be 2 propanol, right? This one's 2 propanol. Right? But they do have common names. You could call this one propyl alcohol. And this one is our old friend, what do we call a 3 carbon chain that has bonding at the center carbon? Iso. Very good. This could be isopropyl alcohol. Unfortunately, I can't tell you which one of these you need to know. I say both. Because you might see this on the exam, and you might see, oh, that's isopropyl alcohol. But then you go and look at your choices, and A, B, C, and D, there's no isopropyl alcohol. It doesn't mean you're wrong. It just means, hey, I got to take another look, and then say, oh, it's also 2-propanol, and then you go and you find 2-propanol in your answer. Isopropyl alcohol, anybody heard of this? What is it?
Like well, I use it as an alcohol swab thing.
Yeah, it's rubbing alcohol,
Yeah.
right? It's rubbing alcohol. This is drinking alcohol. This is rubbing alcohol. Okay. Both of them are toxic, by the way. Ethanol has an MSDS, material safety data sheet. It has issues. It says in there, dangerous. Don't drink. People drink. Some people more than others. Not really. Okay? Everybody good? So, you don't have to locate the OH group in methanol or ethanol. But after that, you pretty much do. If we look at a C4 derivative, let's write it this way so you get to see it different ways. I don't know if I can squeeze this one in. What's this one? What's a 4-carbon chain? Where's the OH? Oh, is that one of mine? Where's the OH? You can't just say butanol, because both of these could be called butanol.
On the first one.
Which makes it
One butanol.
1 butanol. 1 butanol. Notice, OL, 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 that's alcohol, OH group. I have a butane, 4-carbon, with an OH group on carbon number 1. Alternatively, you could call this butyl alcohol. It could be butyl alcohol. Although I don't think we'll probably go that high. Probably stop at propyl and isopropyl. Okay, but they do exist. This one, 2 butanol. See, now the OH group is on carbon number 2. Notice that these are the only 2 forms of alcohol. Because had I put the OH here, it still would have been 2 butanol because I simply would have started numbering from the other side. And if I put the OH here, it's still 1 butanol. So, yeah. 2 butanol. And I know that to be the sec-butyl group. So this could also be sec-butyl alcohol. You don't have to know that. It's a sec. The sec stands for secondary because look at that carbon. Is that carbon a secondary carbon? Sure is. There's the carbon that contains the OH group. It is bound to that carbon and that carbon, which makes it a secondary carbon. And that's what sec is short for. But this is one of the alkyl groups of C4. Remember, C3 had 2, isopropyl and propyl. C4's got butyl, sec-butyl, T-butyl, and isobutyl. And then there are a bunch more at C5. We're only going to ask you to know the C3s, propyl and isobutyl. Okay. If you see these in the open chain or in the line formula, okay, what is that?
1
one butanol, right? It's one butanol. Listen, the common mistake that students always make is they say, how many carbons? 1, 2, 3, 4, 5. And then the OH group. Okay? It's not like that. Here's a CH3. There's a CH2. There's a CH2. There's a CH2. And then off that, I have the bond to the OH. Don't count that as a carbon, because when you see it written in the software actually puts a space between it like that. It ends, and then you have the OH. Don't put a carbon there. That doesn't mean there's an extra carbon there, okay? I know it's deceiving, but once you see it and you become familiar with it, you're good. Everybody see that? You simply count it. 1, 2, 3, 4. No, there's no carbon there. 4 carbon, butane, OH group on carbon 1, 1 butanol. Okay? Substitutions are first. Those out front first. What do we have? Anyone?
3,4-dichloro, 2-hexanol.
2-hexanol, yes. Oh, she's doing her work. No doubt about the fact she's doing her work. What's our longest chain that contains the OH group? Now notice, if I were to put a chlorine even here, I still number from this side because it's not substitutions, it's functional group. Here's the functional group. So, which way numbering puts the lowest number on this carbon? If I go this way, it's 2. If I go the other way, it's 5. So I pick the green way. We're green here. This made it took up. That's a 6. 6 carbon chain makes it a hexane. Got an alcohol on it. Now it makes it hexanol. Alcohol's at carbon number 2. Makes it a 2-hexanol. Substituted groups at 3 and 4. They're both the same. Chloro, dichloro. This is 3,4-dichloro -2 hexanol. Okay? Now you've got the name right here in front of you. It's going to take you about 7 seconds to check it. Hexane. 1, 2, 3, 4, 5, 6. Yep. 2-hexanol. Yep. Dichloro at 3,4. Yep. Good. If you can name it, and then you can act like you were given the name and draw the structure, and you get that structure, you're 100% correct. There's no way it can be wrong. Because you were right, you got this answer 2 different ways. You got it from here, and then you used it to generate back that same molecule. Kind of an independent test. And it doesn't take very long to do that, and I would highly encourage you to do that. Because it doesn't take very long. Okay? It is possible to have 2 alcohol groups on one molecule. We won't see them too often, but if you do, it would be a diol. For example, what if I put an OH group here, for example? And again, we won't see them. You might see one in lab or something like that. Let me get rid of this blue so it doesn't screw people up. Everything would be the same, except it would be 2,3 hexadiol. Notice di to all alcohol. You're not going to see them. I think you run into one in the homework or in the lab or somewhere. By and large, at this level, I tend to stay away from molecules that contain more than one functional group, and even more than one of the same functional group. Okay, let's just concentrate on getting the naming protocols down. Okay, everybody good? You see how everything relates to that alkane protocol? I mean, longest carbon chain, number the chain properly, put the lowest number on the functional group, locate all the substitutions using the carbons that they're attached to, name it. And then we got the little kicker in here that's got the ending. Now the table in the book tells you what the endings are. If you look at them back in chapter 6, 7, sorry, on 7.2, for alcohol, for example, you see how the name ends in OL? So it kind of gives you a hint as to what the functional groups are versus what their names are. Okay, you have to know what is the structure of the functional group. What is that structural similarity that's common to all members of a particular class? You need to know the structure. You need to recognize the structure, and you need to know how to name it. You need to know how to put it into the parent name so that you can tell the reader, hey, these endings translate to structures, right? They translate to functional groups. So when you see something that ends in OL, you're automatically thinking OH group. Okay, they translate. When you see ENE, double bond. When you see YNE, triple bond. Okay? When you see ANE, you know it's alkane. Okay? You really have to focus in on it. Okay. What kind of reactions do these alcohols undergo? Reactions. The first one is dehydration. What happens when you dehydrate? What happens? Yeah, you lose water, right? When you're dehydrated, you lose water. So dehydration, you're going to lose water. Loss of water. Well, if we think of water as being HOH, right? We're starting to piece together where our water is coming from. See that OH group? You seen that anywhere else? Yeah, that's the alcohol functional group, right? So if you have an alcohol, say you have a generic alcohol, and you have a hydrogen on the adjacent carbon, there's your water right there. There's your water. And what's going to happen is the H and the OH are going to go away, and they're going to come down and form a double bond. So we're going to lose water. This should be acid, yeah, acid catalyzed. I have an acid catalyzed, and usually that's going to be H2SO4. Technically, you could use any acid, but sulfuric acid tends to be the more common acid used in these. So I'm just going to put it in. Now remember, this is a catalyst. It's a catalyst. And what do catalysts do? Catalysts make reactions occur faster. They're not magical. They don't make reactions occur that normally would not occur. They just make reactions occur at a faster rate. They increase the rate by lowering the activation energy. The amount of energy to get the reaction going, the catalyst lowers it. That's it. It doesn't take part in the reaction. It's not changed in the reaction at all. However it starts out, that's how it ends up. By definition. If it gets used up in the reaction, it is not a catalyst. It's now a reactant. It's a starting material. Look at that. Alcohol dehydrated to what? Alkene. Remember last lecture? What did alkenes do? One of the reactions for our alkenes, remember we had hydrogenation, we had halogenation, and we had hydration. Remember? The opposite of dehydration is hydration. Right? And it's the exact opposite of this reaction. We took the alkene, we added water, we thought about water in terms of H and OH, and we simply put an OH on one of the carbons and an H on the other. It's the opposite. And it should be. Dehydration is the opposite of hydration. Okay? Anytime you have an alcohol and you have adjacent carbons that contain hydrogen, you can dehydrate. If you don't have any hydrogens here, it's not going to dehydrate. A common mistake is that most students take both the OH and the H from the same carbon. You don't do that. You take the alcohol group and an adjacent H to form the water. Well, this will be that much easier when you go to do this. What do we have? Well, we have our OH group, so we know that's going away. So the carbon that contains the OH group is definitely going to be part of the double bond. Definitely. 100%. The carbon that contains the OH group will be part of the double bond. And technically, you could form a double bond between that carbon and any adjacent carbon that contains a hydrogen. So, this guy could form a double bond this side, because that's got it, or this side. So if we expand this structure and we look at it like this, oops, there's our expanded structure. One product could be here, double bond. The other product, because there's also a hydrogen on the other side, could be there. So when we dehydrate this, we get or right? And here's a case where looking at this thing in terms of the line is so much easier now when you see those. Because now you can say, there's my OH, here's my possible double bonds. Here and here. It's very clear when you see it in the line. So you can look and say, here's one, and here's the other. What's the problem? What's the problem with those? Anyone? Anyone?
Something wrong.
You?
You don't have the OHs on there?
Yeah, well, they're gone. We dehydrated.
No.
What's, name this? 1, 2, 3. What is this? Say it. I'm looking at you.
Propene.
Propene. 3-carbon chain alkene is propene. What's this? Say it.
Propene.
Yeah, it's the same thing. Aren't those the same thing? Just pick this thing up and rotate it 180 degrees. These are the same thing. So you don't have two different products here. Because you have a symmetrical starting material. And that's what we're going to give you. Is it possible to have a long carbon chain over here so that we actually did get two products? Yes. Yes, it is. By and large, the easiest way to do this is to locate the OH group and know that you can draw a double bond between the carbon that contains the OH group and any adjacent carbon that has a hydrogen. Those are your potential double bond positions. Okay? And most of the time, it's going to give you the same thing, at least in here. You're going to get the same one no matter where you do it. Okay? We could even take this one step further. And we could get rid of that. And we could put another CH3 here. Now we're looking at double bonds here, here, and here. But either way, it's always going to be the same thing. Doesn't matter where you put them. We would actually have one more. Put it there, so go here. But these are all the same. 1, 2, 3, 2-methylpropene. Every single one of them. 2-methylpropene. 1, 2, 3, or 3, doesn't matter. 1, 2, 3. Oh, sorry, I got to do that backwards, right? Because you got to number the alkene with the lowest number. Either way you cut it, it's 2-methylpropene. But if I'm looking, I can go here with my double bond. I can go here with my double bond. Or I can go here with my double bond. In the dehydration. Okay? Don't complicate it. We're not requiring you to know the mechanisms. The mechanisms are the stepwise progression that occurs in the conversion of reactants to products. And you can have multi-step mechanisms or you can have single-step mechanisms. Either way, we are not requiring you to know the steps. We just want you to know the start and the end. Predict the products. It's a beautiful question because all you have to do is give the products. You don't have to justify where they came from or what they are. Just find the OH group, get rid of it, go to the adjacent carbon that have hydrogens, remove the hydrogen and put the double bond across. Because you are making water, right? Which means that OH is coming from here. This is the source of the hydrogen for one. This is the source of hydrogen for another water. This is the source of hydrogen for the other one. So you're always losing water. Of course, these would have plus H2O. Right? Okay? Everybody good? All right. Next reaction is oxidation. Oxidation. Here it is again. Back. We haven't even had the exam on it. We're already talking about it again. You guys had the exam. Oxidation. Now, we saw oxidation in the general chem, in the first couple of sections. And we identified redox reactions. It's transfer of electrons. And we said if something gave up electrons and its oxidation number went more positive, right, then that was oxidation. So if it started out at +2 and it gave up some electrons and went to +4, that was oxidation. Right? Here in organic and biochem, oxidation is a little easier for us to grasp because oxidation takes on a different definition. Now, oxidation under the transfer of electrons, oxidation under this definition I'm going to give you, it's still oxidation. There's no violation. Oxidation is oxidation is oxidation. But for us, oxidation is, and this really goes more in line with the actual word, gain bonds to oxygen, lose bonds to hydrogen, or both. The word oxidation, to me, sounds like you're gaining oxygens, doesn't it? Oxidation, gained oxygen. So under this definition, it makes sense. When we look at the oxidation of alcohols, we have to look at primary, secondary, tertiary, because they behave differently. Primary alcohols oxidize. This little bracket with the O means oxidizing agent. There are many, 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 many different types of oxidizing agents. And depending on what your desired product is, you can use different oxidizing agents. And money. Some of them last longer, some have to be prepared fresh. You know, all kinds of things need to be considered. So, we just say any generic oxidizing agent. Right? Something like permanganate is an oxidizing agent. Ozone is an oxidizing agent. Nitric acid is an oxidizing agent. Osmium tetroxide. There's a whole bunch of different oxidizing agents. And they all act differently. They all oxidize in different ways. So we don't generally study the reaction mechanisms that lead to oxidation. We just say, here's an oxidizing agent, and this is what happens. Primary alcohols are oxidized to aldehydes, which are further oxidized to carboxylic acids. Now, we'll be dealing with aldehydes a little bit later on in the lecture, but carboxylic acids, we're just going to have to wait till the next lecture. I know you're going to be okay. All right? You're going to be able to sleep. Oh, I want to go through the carboxylic acid. No, you don't. Okay? So, let's look at a primary alcohol. This is a primary alcohol. The only requirement for us to have a primary alcohol is that the carbon that contains the OH group is bound to only one other carbon. Okay? I'm going to switch this around. No big deal. You don't have to. Just write the aldehyde the other way in a minute. I just want to switch it around just for a little clarity. Okay? I'm going to put a star on my carbon that contains my OH group. Everybody agree that this is a primary alcohol. Everybody can see that, right? You can see that. Terminal alcohols, by the way, where you have the OH group on a terminal carbon, the first carbon, they're going to be primary. Right? Secondary alcohols have to be interior, because they have to have carbons on both sides. So I'm going to oxidize this. Here's our primary alcohol. I'm going to give you a generic oxidizing agent, and this is my product. Again, I'm going to star my carbon that contain my OH group. I'm going to hit this again. And I'm going to star my carbon. Everybody got those written down? Yeah? Okay. Let's look at our carbon right here with our star on it, our primary alcohol. How many bonds to oxygen does it have? 1. How many bonds to hydrogen? Where's the third one? 2. This hydrogen is bound to the oxygen. It's not bound to the carbon. We're only looking at the carbon. Carbon has 1 bond to oxygen, 2 bonds to hydrogen. Let's jump over here. How many bonds to oxygen does that same carbon have now? 2. 1, 2. How many bonds to hydrogen? 1. Did we gain bonds to oxygen? We did. We had 1 over here, and now we have 2. Did we lose bonds to hydrogen? We had 2 here, and now we have 1. We didn't have to do both. Any one of them would have defined oxidation for us. But in this case, we did both. Then I oxidize it again, and I look at this carbon. How many bonds to oxygen does it have? 3, right? Remember, this isn't bound. This is, the OH groups aren't bound to the carbon, bound to the oxygen. So my starred carbon, it's the same carbon all the way through. It's the one that had the oxygen on it. Still got the oxygen. Here I have 1, 2, 3 bonds to oxygen, no bonds to hydrogen. So I did both again. I am oxidized. This is an aldehyde functional group, which we'll see in just a minute. That is your aldehyde. A C double bound to an O, single bound to an H, aldehyde. You'll know that by next week, because you'll memorize it. Yeah, felt the head shaking.
Good.
This is our carboxylic acid functional group. C double bound to an O, just like the aldehyde. C double bound to the O. But instead of one of the remaining bonds to carbon, carbon's only got 4 bonds, right? Right off the bat, the C double bond O takes up 2 of them. So it's only got 2 left. For the aldehyde, one of those must be to hydrogen. For the carboxylic acid, one must be to OH. We'll learn them. We're not there yet. Okay, we're studying alcohols. It just so happens that in the reactions of alcohols, we produce functional groups that we haven't studied yet. Just like we did with alkenes. Remember, we hydrated an alkene, we produced an alcohol. We just didn't know it yet. Okay? Primary alcohols oxidize to aldehydes, which quickly oxidize to carboxylic acid. In fact, there's very little of this present at any time. You have to use special reagents if you want to stop this at the aldehyde intermediate. Primary alcohols oxidize to aldehydes, which further oxidize to carboxylic acids. Secondary alcohols. Secondary alcohols oxidize to ketones. Again, ketones we'll see at the end of this lecture, but right now we don't know what they are. So in order for us to have a secondary alcohol, the only thing that's required is that we have a carbon containing the OH, and that carbon is bound to 2 other carbons. Secondary alcohol. If we hit that with an oxidizing agent, we have a ketone. That actually is the ketone functional group. A C double bound to an O, notice that both aldehydes, carboxylic acids, and ketones all have a C double bound to an O. Call that a carbonyl group. We'll see that in a little bit. But the 2 remaining bonds have to be to carbon. They have to be to carbons. It can't be to hydrogens or OHs or anything else. They have to go to carbons. And you have yourself a ketone. Look at my carbon that I start. How many bonds to oxygen over here? 1. How many hydrogen? 1. How many bonds to oxygen? 2. How many bonds to hydrogen? 0. I gain bonds to oxygen and lost bonds to hydrogen. That's oxidation. So you can look at things now. Okay? You can look at things and you can say, primary alcohol to carboxylic acid, that's oxidation. I don't really know how it happened. I don't really know why it happened. But I see the carbon that contains 1 bond to O now has 3 bonds to O, oxidation. Okay? Everybody good?
How do you write the formulas of those?
We wouldn't show them as molecular formulas like C15. We wouldn't do it that way. We show them CH3, CH2, or in the line formula.
Right.
That's how. We're going to do examples. Well, not necessarily real examples of these oxidations, but we will when we see aldehydes and carboxylic acids, and just not carboxylic acids, just the aldehydes. Okay, so we did primary alcohol, secondary alcohol. What's left? Tertiary alcohol. This is your favorite. All students love oxidation of tertiary alcohols. In order to have a tertiary alcohol, this is what we need, right? There's our tertiary. So I can put my little lines on there, but I don't want to clutter it. In order for us to have a tertiary alcohol, we must have a carbon containing an OH group, and that carbon must be bound to 3 other alcohols. When we oxidize this, you know what we get? Nada, zippo, goose egg, zilch. NR. No reaction. Tertiary alcohols do not oxidize. Yes.
Is it because it's not bonded to any hydrogens? Is that why?
That's exactly right. Which is right where I was going. If you look at the tertiary alcohol, you see that the carbon is only bound to carbons. There's no hydrogens there. Look what was happening when we were forming or oxidizing. We were forming additional bonds to oxygen, right? At the expense of bonds to hydrogen. So we were forming carbon-oxygen bonds, but we were breaking carbon-hydrogen bonds. The carbon-oxygen bond is stronger than the carbon-hydrogen bond. That's why it works. The weaker bond, CH, is broken, and the stronger bond, CO, is formed. Here, in order for us to create a potential double bond here, it would require us to break what? The carbon-carbon bond. That's the only thing we have to break. The carbon-carbon bond is stronger than the carbon-oxygen. So you can't form a weaker bond in favor of breaking a stronger. It increases the overall instability of the molecule. It won't do it. Okay? So, in order for you to oxidize a carbon. Now notice, remember I told you before, formulas aren't oxidized. Individual atoms are oxidized, right? It's this carbon that's oxidized, not this whole thing. It's this carbon, not this one, not this one, it's this one. In order to oxidize a carbon atom, that carbon must have at least one hydrogen bound to it. Okay, that's a general rule. That's the general rule. And this is all just about bond dissociation, bond breaking energies. Weaker bonds will break in favor of the formation of stronger ones. If it's very hard to break a bond, it's very stable. It doesn't want to break. If bond breaks real easy, that's a weak bond to begin with. Okay? Okay? We good? So our alcohols undergo dehydration to produce alkenes. Alcohols undergo oxidations, which depends on whether you have primary, secondary, tertiary. Primaries oxidize to aldehydes, further oxidize to carboxylic acids. Secondaries oxidize to ketones. Tertiaries, nada. Okay? These alcohols are really good starting materials because every one of those reactions that I just told you was a change in class. Alcohols to alkenes. They dehydrate to alkenes. That's alcohol class to alkene class. Alcohols to aldehydes. That's a different class. Carboxylic acids, different class. Alcohols to ketones, different class. So all those reactions result in a change from alcohol's functional group into some other functional group. It's very valuable. Questions? You gotta know these, right? Gotta know these. Okay. Next, let's take a look at phenols. Phenols. Now, the extent of our study of phenols is going to be just in nomenclature, just naming, okay? We're not going to go into any reactions involving phenol. Now, phenol we saw from the end of last lecture is a benzene derivative, right? And more specifically, it's a benzene with an OH on it. This is phenol. Now, if you have phenol, if you see benzene with an OH, you're going to want to name it as a phenol. And when you do, you automatically have called this carbon number 1. No matter what, you don't have a choice anymore. If you're going to name it as a phenol, the carbon that contains the OH group has to be carbon number 1. So if we substitute onto our phenol, this is carbon number 1, this must be carbon number 2. We still want a number in the direction of the substituted group. We don't want to go 1, 2, 3, 4, 5, 6. So this would be 2-methyl phenol. 2-methyl phenol. All one word. Okay. It doesn't matter how many you have. It's 4. What's substituted at C4? What's this one?
3 bromo 4 ethyl.
Yep. I got 2 choices here. I can number this way. 1, 2, 3, or I can go 1, 2, 3, 4. Going this way, just so happens going that way puts 4 on it, right? Going this way puts my first substituted group lowest number. So this is 4 again, no matter which way you go. I have 2 groups, bromine, bromo, and ethyl. B comes before E in the alphabet. This is 3 bromo, 4 ethyl, phenol or phenol. Okay. Now remember benzene. When I drew that, or I made that with the model kit and I showed it to you, it's flat. It was C6H6, right? Alternating single and double bonds. So the phenol has 5 hydrogens here. You can remove a hydrogen from phenol and create an alkyl form of phenol. You can create an alkyl form of phenol. And we call it, just like all alkyl forms, it ends in YL. This is phenyl. I know it's close. Phenyl. Phenol. It's close. It's the phenyl group. Alkyl forms, I'm sorry, the alkyl form of phenol is not phenyl. The alkyl form of benzene is phenyl. Sorry, guys. Got all caught up. That's benzene, where we remove an H and create a point of attachment. It's phenyl. Right? Everybody got that? The alkyl form of benzene is phenyl. See, there's no OH on it. Let's see OH. So this would be 1, 2, 2-phenyl phenol. Ugly. 2-phenyl phenol. Everybody see that? Again, you're going to see phenol on the exam, some way, shape, or form. Okay, you just have to memorize it as the OH form of benzene, the OH substituted benzene. Right. And again, no reactions with phenol. Because it's benzene, it's unusually stable. It does undergo substitution reactions. They're called electrophilic aromatic substitution reactions. But we're not going to cover it. We just want you to know how to recognize a phenyl group, phenol, and how to name them. Okay. Esters.
Alright, so, like the work examples on 810, that's more than we need to really know.
Yeah.
I started seeing stuff like that, I'm like, that's it, I'm done with the chapter.
No, yeah. Those big, hairy examples there on age, looks like 810, yeah. Mint and savory. Those are just examples to show you some multi-substituted phenols.
Should we memorize those?
No, you do not need to memorize those. I'm just wondering if any time in the future you will, and we're videotaped, so sometime in the future. Okay, I'm going to say for my classes, no. But if you're in anybody else's class and you're watching this video, everything's fair game. My classes, no. Okay, esters. No, ethers first, right? Yeah, ethers. Someone raise your hand, tell me. I'm getting tired. Aren't you guys getting tired of this? Ethers.
I heard the word about esters.
Esters, yeah, esters aren't until the next chapter. Now, long.
I thought you were just pronouncing it.
You're just going to skip some things? Jump to unit 8 or whatever, 9, whatever. Ethers. The functional group for an ether is an alkyl group connected to another alkyl group through an oxygen. Now, I'm going to put a prime on this alkyl group, meaning these don't have to be the same thing. Remember what an alkyl group is, okay? Because you see these R groups, and this is, most of the time, much of the misunderstanding with related to organic chemistry is because you don't understand the terms of the letters or whatever there is there up on the board. Remember the alkyl groups, things like methyl, ethyl, propyl, etc., etc., etc. It's just an alkene minus one hydrogen. It's an R group. That's all it is. Any alkene minus one hydrogen has the potential to be connected here. All right? And again, I put a prime here because I'm saying these two don't have to be the same alkyl groups. They can be, but they don't have to be. Okay? You can see the ether functional group very clearly because this is the very first time that we've interrupted our carbon chain with a heteroatom, a non-carbon atom. We're cruising along here, nice, here's our carbons, all of a sudden we say, what the heck? What's the oxygen doing in here? Why is that breaking the sequence of my continuous carbon chain? This is your ether. This is how you know you have an ether. Okay? Naming ethers is very straightforward. It actually doesn't require you to know any additional stuff except the word ether, which you now know because I just gave it to you. You take your oxygen, you find it, you draw a line right through it. If you have an ether, you just separated your molecule into two alkyl fragments. Name the alkyl fragments. What is this one? Ethyl. What is this one? Propyl. Propyl. Not isopropyl, right? Because it's a terminal carbon. Propyl. Alphabetize them. End it with the word ether. This is ethyl, propyl, ether. Ether is pretty straightforward in naming. Pretty straightforward. Mixing conventions a little bit, right? Let me draw that. Then I'll show you. It's like little stick people now, huh? What is this? Very good. Yes. Yep, everybody see it? Let's draw a line through our oxygen. We have ethyl. This, 1, 2, 3, 3 carbon chain. where we're attached at the center carbon. In unison. Isopropyl. Remember I told you the isopropyl group looks like a Y. That's a sideways Y, but it still looks like a Y. Alphabetize. Ethyl isopropyl ether. It's like a little spider, huh? Coming after you. Yep. Getting this? No. What is this? Anyone? Diethyl ether, right? Ethyl, it's not ethyl ether. It's diethyl ether. Okay? Diethyl ether. No? One's 5, one's 6. What is this one? Take a crack.
Hexyl pentyl.
What?
Hexyl pentyl ether.
It's not hexyl. What is it?
Oh, cyclohexyl. Okay.
Keep going, you got yeah.
Cyclohexyl, cyclopentyl ether.
Yes. Any alkyl group will work, okay? These are, remember, our cycloalkanes. This is cyclopentyl, okay? Cyclopentane. There's cyclopentane. And then you remove a hydrogen and create a point of attachment. It's cyclopentyl. Drop the A and E, add YL. You're still creating the alkyl form of an alkane. Obviously, they both have cyclo, so the alphabetizing is not going to start there. It's going to go P to H, right? So what did you say first?
Hexopentyl ether.
Go. Cyclohexyl, cyclopentyl, right?
Yeah.
Okay. Cyclohexyl, cyclopentyl ether. It's a long name. Any alkyl groups can be used in ethers. Oh, yeah. Okay, let me just look at it this way. See it?
Here with that.
See it? You switch them around. What's this one? Ooh, setback, huh? The method for naming ethers that we use for the alkyl, breaking them up into the alkyl forms, is usually for what we call simple ethers. Unfortunately, they're not all like this. Now, we don't cover this in the book, but I'm just giving it to you because you paid your fees. You're entitled to a little extra. So, when you do this, when you see this stuff, you treat this as a substituted group called an alkoxy group. So this would what we call methoxy. Methoxy. It's nothing more than an alkyl group with an oxy on it. So methoxy, ethoxy, that's usually as high as it's going to go. And you just treat it as if it were a substituted group. 1, 2, 3, 4, 5, 6. This is 3 methoxy. 1, 2, 3, 4, 5, 6. Hexane. 3 methoxy hexane. Okay, I just want you to be aware that there are other forms out there. And it seems to me that you run into one somewhere. Whether it's in the lab or in the book or in one of the online resources, somewhere. It seems to me you ran into it. I could be confusing it with 206, but it's easy enough. On the exam, you're going to be dealing with alkyl, ether, for sure. Simple ethers. Alkyl, ether. But there are other ethers out there. The problem is you don't know, you know this is methyl well enough, but you don't know what the heck alkyl form that is, right? So, we use this, the alkoxy method. Okay? Questions? Okay. No reactions for the ethers. There are several out there, but we're not going to learn any. Okay, you see how important the nomenclature is becoming, right? All right? Think about all the functional groups, okay, that we've done already. We've done alkanes, alkenes, alkynes. We've done alcohols, phenols. We've just done ethers. We're going to do aldehydes and ketones next. That's 8. Then we have esters, carboxylic acids, amides, amines, aromatics. We already did aromatics, right? So you're looking at 13 off the top of my head. 13 functional groups. 13. Right? If you get a structure and you have to name it, and the name and you have to pick the structure, for each one of those, that's 2 questions apiece. That's 26 questions right there out of 40. Right? And then let's say half of these, you have a general question. Like, for example, alkanes, maybe, what's the general formula of an alkane? CnH2n plus 2. Let's say that you just have general questions, an additional general question on half of these. Let's say another 6, 7. That's 32 questions. 32 out of 40 directly related to chemical nomenclature, to naming. That's over 75% of the exam. You know your naming protocols, you're passing this exam. 100%. I guarantee you're not going to get 100%. I'm saying 100% you're going to pass it. If you know your naming protocols. Just the math. And then let's say you have 6 or 7 questions, or 8, related to a couple of the reactions. Oxidation of alcohols, whatever. Okay? You can see the importance of knowing the naming protocols. And you see how fast they're coming at you. You've got to stay up. You've got to keep up. Okay. It's after ethers. Aldehydes. aldehyde. The aldehyde functional group looks like this. It has a C double bond O, which is called a carbonyl group. It's called a carbonyl group. The carbonyl group requires a carbon double bound to an oxygen. Since carbon can only have 4 bonds, 2 of them are well defined or invariant, which means in the carbonyl group you only have 2 bonds left for you to put various substitutions onto the particular molecule. For the aldehyde, one of the bonds of the carbonyl carbon is taken up to hydrogen. If you have this, you have an aldehyde. Okay? Now, the carbonyl group is very polar. It's very polar. The electronegative oxygen pulls the electrons. Now, you have a double bond here, right? Double bonds are twice as many electrons. Remember, each bond is 2 electrons. So, the single bonds, there's 2 electrons between the 2 atoms, but a double bond, there's 4. There's twice the electrons, right? The double bonds are shorter and stronger, right? So, carbonyl groups are polar. Polar. Differences in electronegativity between oxygen and carbon relate to an uneven or asymmetrical distribution of the electrons. They're more on the oxygen because it's closer to fluorine. That gives it a slightly negative charge. The carbon slightly positive. Naming aldehydes. We're going to drop the E. Sounding familiar, right? From the alkane parent. And we're going to add the suffix Al. No, the word aldehyde starts with Al. I know, so all the aldehydes end in Al. It doesn't make a whole lot of sense. But you got to relate them somehow. It doesn't end in YDE. First couple of aldehydes. Notice here that I did not put an R group. Okay? You'll see R group here in probably 95 out of 100 textbooks that you look at. Because most of the time it's true. But there is an aldehyde that has another hydrogen bound there. The first one. Okay, so our first one looks like this. And we would call that methane. Drop the E at Al. Methanol. Notice how close that is to methanol, the alcohol. Methanol, methanol. You'd think those IUPAC guys, while they're in Switzerland or something, would, make those a little bit more different. Is that a word? 2 words? Methanol. However, I've never seen it called methanol. I know it more by its common name, formaldehyde. Formaldehyde. This is the fluid that they preserve dead people or dead things in, right? Grasshoppers and pigs and whatever. Formaldehyde. anyone who's ever been around formaldehyde knows that it stinks. Okay, you cut your cat up in biology or whatever it is, you go home and that stuff's in your clothes, it's in your skin, you can't get rid of it. No matter how many times you shower. This is organic compounds. This is just how they are. Most of them smell nasty, some of them smell good. Oh, also, this particular group can be represented CHO. Okay, I left that out. I want to show you that. CHO. It can't be COH, right? It can't be COH. Then you might mistake it for what? A what? An alcohol, right? COH. You might mistake it for an alcohol. So CHO is the shorthand version. Here is the C2, which would be what? Ethane, ethanol. Again, common name here. This one's known almost exclusively by its common name, acetaldehyde. Sorry, you gotta know. You gotta memorize. Sorry. After that, pretty well behaved. I'm just showing you it in a different way. With the CHO. 1, 2, 3, what would you call this? Propanol. After that, they're pretty well behaved. You can have substitutions on your aldehydes. Take a crack at that one.
3-chlorobutanol.
What about the aldehyde group? Where is it? Where's the aldehyde group? What carbon number? 1. Can it ever be anything other than carbon number 1? No, it can't, right? Look at the aldehyde functional group. Carbon only has 4 bonds. The aldehyde group defines 3 out of the 4. It says that if you're an aldehyde, you're going to have 2 bonds to oxygen and 1 bond to hydrogen. That only leaves 1 bonding position left. Which means in any aldehyde group, the carbonyl carbon will always be carbon number 1. You don't have to label it. You don't have to locate it. We number our carbon chain with priority given to the functional groups. We always have, outside of the alkanes, right? Because the alkanes didn't have a functional group. Aldehyde carbons are always carbon number 1, no matter what. No matter what. So you never have to locate them. It's not 3-chloro-1-butanol. Okay? You never have to locate it. Everybody good? See why it's 3? This is carbon number 1, 2, 3. Chloro group of carbon 3. All right? Reactions for aldehydes. We already know one, don't we? Aldehydes. Oxidation. We know that aldehydes oxidize. Aldehydes oxidize carboxylic acids. Right? That's the second part of the primary alcohol part, right? Primary alcohols oxidize to aldehydes, oxidize to carboxylic. So we have our aldehyde group. We oxidize it. We get our carboxylic acid. Again, there's our, don't know this one yet, but we will. A particularly common example of the oxidation of an aldehyde is Tollin's test. And we're going to be doing this in the laboratory. This is often called silver mirror test. Tollin's test or the silver mirror test. If you have an aldehyde in solution, the Tollin's reagent is a complex of silver ion and ammonia. Okay, it's silver ion in ammonia. If you have an aldehyde, here it is. This is Tollin's reagent. The aldehyde will oxidize to the carboxylic acid, the corresponding carboxylic acid. In reality, this will be deprotonated. In reality, it's going to be a carboxylate. We'll see later. That a carboxylate is nothing more than the carboxylic acid without its H, right? I just didn't want to throw too much unknown stuff at you. If something oxidizes, notice here our carbon has 2 bonds to oxygen, 1 bond to hydrogen. Here it's got 3 bonds to oxygen, no bonds to hydrogen, oxidation. If something oxidizes, something must reduce, and it's actually the silver plus ion. I could actually stick this over there. It's the silver plus ion that reduces to silver 0. And this plates out. This plates out on the inside of the test tube, and you generate a mirror finish around the solution. So when you're looking at the bottom of your test tube, you're looking through glass, it's clear, and all of a sudden it's a mirror, and you can see yourself. It's pretty cool. Before you get any bright ideas about getting a bunch of aldehydes, taking a bunch of Tollens reagent, making a bunch of silver, all right? The Tollens reagent's more expensive than the silver. So your company and your idea. Okay, I already thought of that. Thought, hey, if I get everybody and then scrape it off, in about 30 years I might have, I don't know, a milligram. Okay, it's a particularly common example, and we're going to do this in lab. We're actually going to perform this experiment in lab with different aldehydes and ketones, which test negative because you have to have an aldehyde. Ketones test negative because ketones don't oxidize. All right, any questions? No? Not yet, right? We didn't get home yet. All right, last one, last group. Ketone. The ketone functional group. Now put a prime on here because, again, the alkyl groups. Remember, alkyl groups are just alkanes minus a hydrogen. We have a lot of different types of alkyl groups. The ketone has the carbonyl group, the C double bond O. So 2 of the bonds are defined. The remaining 2 bonds on carbon, on the carbonyl carbon, must be to other carbons. That's a requirement to be an aldehyde or a ketone. Okay, you have to be bound to carbon. So a lot of times you can see this thing written like this. You have to have carbon here. What comes on after on both sides doesn't matter, but you have to have carbon. All right, the carbonyl group is common to a lot of different functional groups, 4 or 5 of them. We've seen it so far in 2, right? The aldehydes and now ketones. We actually saw it in carboxylic acids, but we didn't study that yet. We'll see it in esters and amides, 5 of them total. So it's a pretty common structural feature. If your carbonyl carbon is bound to other carbons on both sides at the remaining 2 bonds, then you have yourself a ketone. When you name ketones, you drop the E, from the alkane parent, and you add the suffix "-one". Note, ketone. So the word ketone ends in O-N-E. So do the IUPAC naming for ketones. Now our first ketone is at the C3, right? Why? That's right. If you have to have a C double bond O and it's got to be connected to carbons on both sides, the smallest alkyl group is the methyl. So if you put methyls on both sides, 3 carbon is the first member of the ketone class. This would be called what? Drop the E. 1, 2, 3. What would it be? Propane, drop the E, add O-N-E, propanone. Okay? Unlike the aldehydes, the carbonyl carbon cannot appear on an end carbon in a ketone class. You can't see this on the end. If it's on the end, that means that one side isn't bound to a carbon. Therefore, not ketone. Okay? I've never seen it called propanone. It's almost 100% named using its common name, acetone. Most of you know this as the major component in nail polish remover. Assuming you put nail polish on your hands. What's this? Butanone. What's this? Huh?
Hexanol?
Pentanone? What's that? You see 5 now? I see 6. Making carbons of it. What's this one? ISO is only going to go with propyl for us. That one's pentanone too, right? Right. Once you get past a certain number of carbons, and that number is 4, once you get to 5, you have to locate the carbonyl group. 1, 2. This is 2 pentanone. Which would make this one 3. Pentanone. There is another method for naming ketones, a common method. Okay? And in that method, we treat it almost like we're naming ethers. We find the carbonyl group, and we draw a line through it. We have alkyl groups on both sides. We name the alkyl groups, alphabetize them, and end with the word ketone. So this is methyl. 1, 2, 3. This is propyl. ketone. M comes first. Methylpropyl ketone. What's this one? Diethyl ketone. Who said that? You're good on those diethyls, right? Diethyl ketone. 2 words. Diethyl ketone. I wish I could tell you which one is going to be on there.
Well, you could.
Well, the simple ones are probably going to be this way, but we'll do some examples, right? Once you start substituting on there, you can't use the alkyl. There's no alkyl name for this. So we'll do a couple examples before we finish up. Using the IUPAC name, this would be butanone, right? And we don't have to locate it because it can only be here and here. And when you say butanone, it's going to be on the second carbon, no matter which side you're coming from. Alternatively, this could be ethyl methyl ketone. Okay? I think that's kind of funny because this is a pretty good solvent used in the automotive industry, and they call it MEK. They call it methyl ethyl ketone, but that obviously is incorrect because it needs to be alphabet. Those darn automotive guys. What's this one? 4-chloro-2-pentane. 4-chloro-2-3. Yep, looks good to me. Is that what everybody had? We see our carbonyl group. We have to number our chain from the side closest to the carbonyl group, or we're going to number it to give the lowest number on the carbonyl group, which means this side, chloro group at C4. This is 4-chloro-2 pentanone. Again, I think it's easier if you're given the name and you have to draw the structure. I have a pentanone, pentane, 5-carbon chain. One tells me ketone. Where is it? It's at carbon number 2. I also have a substituted group at carbon number 4, and it's chlorine. So I think given the name and writing the structure is easier to do in some cases than looking at the structure and trying to. What's that one?
One 3-chloro, 2 heptane. 1,4-chloro. Oh.
1,4?
No.
Here, let me expand it.
I see it, yeah.
1, 2, 3, 4, 5.
I drew an extra line on my paper.
Oh, you did? You didn't interpret that as being an N and then calling it a carbon?
No, I had a line going, I had another one on the left side.
Right? Don't get messed up here. There's not 1, 2, 3, 4, 5, 6 carbons here.
Yeah.
Only 5. Okay? Is that what you did too? Or did you count that? Did you draw an extra one, or did you count that as a carbon? Yeah, that's such a common mistake, okay? I want everybody to understand that. This N is nothing more than a bond that connects to the carbon. There's not another carbon there. So in this case, you're going to number from the side closest. This is carbon number 1, 2, 3, 4, 5. There's not a carbon here. All that is the bond that connects this carbon to that chlorine. I mean, you got to end it, right? I mean, the bond's got to end. So what is it?
So then it should be 1, 3-chloro, 2 pentanone.
1, 3 dichloro, 2 pentanone. So you're getting a little bit more familiar with seeing them in this line formula, right? I've seen a lot of examples. And there'll be a lot of examples, especially the bigger molecules. The bigger they get, the more the tendency to go toward this skeletal or line structure. Okay, reactions. For ketones, you guys will like this one the best, right? None. None. Ketones don't undergo oxidation, right? Right? We have ketone. that will not oxidize. Just like the tertiary alcohols, right? In order to oxidize this ketone, it would require us to break the very strong carbon-carbon bonds. That won't happen. So ketones, just like tertiary alcohols, will not undergo oxidation. Ketones do undergo different types of reactions, like electron-rich species attacking the slightly positive carbon, but we will not cover those. Okay. Question?